I am Kalaichelvi, Assistant Professor of Chemistry, JJ College of Arts and Science, Pudukkottai. Now we have discussed about fluorine-19 NMR spectroscopy. First we have to know what is meant by spectroscopy. So it is an analytical tool to determine the structure of unknown compound. It is defined the interaction between electromagnetic radiation with matter. The electromagnetic radiation consists both electric field and a magnetic field. In NMR, we have to use radio frequency as electromagnetic radiation. When we pass radio waves to the nucleus, resonance takes place between a nucleus and EMR, that is radio frequency. Depending upon the nucleus, NMR classified into many types. Example, proton NMR, C13 NMR, F19 NMR, Press 31 NMR, etc. Today we have discussed about only fluorine-19, that is F19 NMR spectroscopy. Fluorine-19 NMR spectroscopy, it is a resonance, is an analytical technique used to identify fluorine-containing compounds. F19 is one of the most important nuclei for NMR spectroscopy. The NMR condition is the nucleus should have spin value. If the nucleus does not have spin value, means that is inactive nucleus in NMR. So the fluorine having 1/2 spin value, so fluorine is active compound in NMR. So the fluorine-19 has a nuclear spin of 1/2 and a high magnetogyric ratio, which means that its isotope is highly responsive to NMR measurements. Furthermore, F19 comprises 100% of naturally occurring fluorine. Because of its favorable nuclear properties and high abundance, F19 NMR measurements are very fast than compared to proton NMR spectroscopy. The reference compound for F19 is CFCl3. The other reference standards are trifluoroacetic acid and trifluorobenzene. In CFCl3, having the delta value 0. The trifluoroacetic acid having the delta value minus 76.55 ppm. And trifluorobenzene have the the chemical shift value minus 164.9. So this is a chemical shift. Fluorine-19 NMR chemical shifts are more difficult to predict than proton NMR chemical shift. Fluorine-19 NMR shift are strongly affected by contributions from electronic excited states, whereas a proton NMR shift are demonstrated by dimagnetic contributions. Variation of the effective value of BO, that is external magnetic field, that is radio frequency, experienced by nuclei because of their different electromagnetic environments in the molecule. Usually reported in parts per million of applied field or frequency relative to a resonance in a reference compound CFCl3. Chemical shift of fluorine-19. Fluorine-19 NMR spectra can be performed in a way equal to proton NMR. Chemical shift of organofluorine compounds using CFCl3 as standard range from 50 to 250 ppm. A maximum range is as wide 900 ppm, much wider than proton NMR, which ranges 10 to 20 ppm at best. F19 spectra is very much more sensitive to the structural and environmental changes of molecules. These are the factors affecting chemical shift of fluorine. To compare proton NMR, some of the factors are affected the chemical shift value. For example, inductive effect, van der Waals deshielding, anisotropic effect, Likewise, in F19 NMR, these factors are affected the chemical shift value. One is solvent effect on fluorine chemical shift. Second one is isotopic effect on fluorine chemical shift. And third one is steric deshielding of fluorine. First, we can discuss about the solvent effect on fluorine chemical shift. There will usually not be much variation observed in fluorine chemical shift for the three most common solvents used for obtaining. That is CdCl3, DMSO and acetone. As can be seen in the data presented in table for spectra of a series of typical fluorine containing compounds in various solvents. And the second effect is isotope effect on fluorine chemical shift. Because fluorine is relatively sensitive to environment and has such a larger change of chemical shift, considerable changes in chemical shift can be observed when a nearby atom is replaced by an isotope. For example, the C12. C12, the abundance is very low, so it is substituted by C13 for the atom to which the fluorine is attached, give rise to quite measurable shift, usually to lower frequency. Steric deshielding of fluorine. Another significant and not infrequently encountered impact on fluorine chemical shift is the deshielding influence of alkyl or aryl group attached with it. This deshielding occurs only when there is direct overlap of the van der Waals radii of alkyl group and that of the fluorine. And the deshielding is thought to be a result of van der Waals forces of the alkyl group restricting the motion of electrons on the fluorine and thus making the fluorine nucleus respond to the magnetic field as if the electron density were lowered. The most common situation where this effect is seen in comparison of E and Z isomers of trifluoromethyl or difluoromethyl substituted alkenes. Next we discuss about the coupling constant of fluorine. What is a coupling constant? Coupling means the nucleus coupled with the neighboring nucleus. Okay. So the fluorine is coupled with the neighboring atom. It may be a fluorine or other heteroatoms. So the spin-spin coupling takes place. After that a splitting takes place. The splittings may be a singlet, doublet, triplet, quartet. It depends upon the neighboring nucleus, number of neighboring nucleus. Fluorine like hydrogen gives characteristic coupling constant depending on a spatial displacement and number of bonds between a coupling partner atom. So the coupling takes place, the distance between the two adjacent peaks in the multiplet is called coupling constant. The coupling constant is denoted by the letter J and the units are Hertz. So this is an example for long range coupling, FF coupling. So olefins involved gives this long range coupling of fluorine-fluorine. So this is a fluorine-fluorine coupling, that means homo coupling. Homonuclear coupling constants between fluorine atoms are usually relative large compared with those between hydrogen atoms. So hydrogen coupling constant is lower. So coupling between germinal fluorines also give a large value of 250 to 300 Hertz, but varying greatly depending on environment of the fluorines. 3-bond coupling, 3J, is saturated aliphatic hydrocarbons are usually 15 to 16 Hertz range. But FF coupling constant usually decreases as we increase the number of proximate fluorines or other electronegative substituents. The coupling constant 3J of a trans difluoroolefin is larger than that of cis olefin. The largest 3F are observed between trans vinyl chlorides where the coupling constant is large than 35 Hertz. So this is a heteronuclear coupling. Heteronuclear coupling means the fluorine coupled with the other heteroatoms. A typical coupling of organofluorine compound is observed in a geminal coupling, that is 2J coupling, with a geminal hydrogen being as large as 50 Hz. This coupling can also be observed by proton NMR. This is a heteronuclear coupling. Coupling between fluorine and carbon is also unique in C13 NMR. J1 coupling ranges from 250 to 300 Hz. Generally, coupling constant of J1, J2, J3 and J4 are respectively 16 to 370, 30 to 45, 5 to 25 and 1 to 5 Hz. This fact is a reliable criterion for the determination of fluoroolefin configurations. Next, we discuss about the applications of Fluorine-19 NMR. Organofluorine compounds and consequently F19 NMR have very important roles in research at the chemical and biological interface. In addition to direct applications of organofluorocompounds that are used as pharmaceuticals and agrochemicals, they are employed as props to explore enzyme mechanism, metabolic pathways and biomolecular interactions. F19 magnetic resonance imaging, that is MRI, is a variable alternative to proton MRI. The sensitivity issues can be overcome by using soft nanoparticles. Applications include pH, temperature, enzyme, metal ion and redox responsive contrast agents. They can also be used for long-term cell labeling. Thank you.